introduction and welcome to my talk on TMR angle sensor calibration with 3D misalignment compensation. So tunnel magnetoresistive angle sensors, or in short TMR, have been around for some time. They have found wide application not only in the automotive industry, but also in consumer electronics. They offer certain advantages, such as high sensitivity, also low power consumption and a small geometric footprint. However, there are some drawbacks. For example, compared to Hall-based solutions, they are quite expensive and they also show poor stray field immunity. And in this talk, I would like to concentrate on developing an efficient calibration routine in the presence of misalignment or a constant stray field, because whether we are talking about the practical application or research, misalignment and stray fields always cause artifacts in the sensor's response, and we would like to exclude them in order to better understand TMR behavior. I will start by introducing a very simple model that describes the TMR's behavior under 3D rotation, and then I will use that model to extract the misalignment angles, and then building on that I will introduce a new calibration process that is based also on some statistical considerations. I will then show some optimization results, how they influence the achieved angle error, and I will also compare the new method with a more conventional calibration method. Now the device of interest in this study is a commercially available and fully analog TMR angle sensor produced by TDK, as shown in the center of this coordinate system here. It consists of TMR elements arranged in two Wheatstone bridges, such that if a magnetic field is applied in the XY plane, one of those bridges will measure the X component of the applied field, while the other one will measure the Y component. And in an ideal world, they would produce a perfect sine wave and a perfect cosine wave, and by using those 2 points of information, we can get the angle uniquely by taking the Arcus tangent. In addition, this model also assumes that the response function indicated by this sphere does not depend on the polar angle. So if I record the response under 45 degrees, theta equals to 45, I will still get a perfect sine wave. Now there are multiple sources of potential error. For one, the TMR could be misaligned, so the sensor's coordinate system is not aligned with the coordinate system in which the magnetic field is applied. But there also can be bridge mismatch, so that those two bridges are not perfectly similar in terms of gain, offset, and phase. So if I write them in this general form, they could have a different amplitude, different phases, and different offsets. And a calibration routine should, in addition to those misalignment angles, also determine those waveform parameters, because error in those waveform parameters will also cause error in the overall angle. In the following, I will just concentrate on one of the bridges because the other one behaves exactly the same, just rotated by 90 degrees. Now, for the first case, where the TMR angle sensor is misaligned, indicated by this new orange coordinate system, we have a situation that can be described by a rotation matrix or by 3 Euler angles, alpha, beta, and gamma. And they are not completely independent of the waveform parameters I showed earlier, because actually the phase of the bridge can also be written as a sum of 2 of the Euler angles. But the important takeaway from this slide is that the response function, if the TMR is misaligned, is no longer perfectly sinusoidal. And actually, if you look at the residual, it turns out there's a second harmonic now on top of the sine wave. And not only that, if you do a small angle approximation, it turns out that there are actually 3 main contributions. First, a perfect sinus, then a second harmonic that also depends on the polar angle, so it gets stronger towards the poles, and also an offset that depends on the polar angle. And those 3 components can be summarized in this basis. The first 2 components describe a sinus that can be phase shifted. The third and fourth component describe the second harmonic component that is also dependent on the polar angle theta. And the last component is only dependent on the polar angle, but not on the azimuthal angle. It follows that the new bridge output can now be written as a scalar product of the basis functions with a weight vector. And if you do the small angle approximation, it turns out that the information about the waveform parameters and the Euler angles is already contained if you do a linear fit, and you can extract estimates for all those parameters. However, this was only a small angle approximation of second order, so if you need more precise results, you can use those values as starting values to compute the problem numerically. Now, if I want to design a more efficient calibration routine, what I basically want is to precisely compute W using as few magnetic fields as possible. In this case, I chose to apply n equals 6 fields, and now the question is, under which angles do I have to apply those fields in order to calibrate my sensor? And I can start by formulating the predicted variance, which can be written as a sum of two terms. The first one is the variance of the measurement device. This can only be improved by buying a better measurement equipment. However, the second term is a weighted covariance matrix, and this weighted covariance matrix is a function of this matrix X, and this matrix X includes the angles of the magnetic field that are applied in the calibration process. So by choosing decent calibration angles, I can actually minimize the second term. And now, in order to get the figure of merit, I can just integrate the predictive variance over the whole region of interest. And then I optimize this figure of merit. Now, if you perform that optimization, it turns out that the solution looks like this. So I have 6 red points here, indicating the 6 fields that are applied in the calibration, and they form kind of a symmetric prism. Now, if I didn't know about this second harmonic behavior or the offset, I could just naively apply fields on the equator of the response function in order to get my sensor response function. And then in the following, I will compare those two cases to one another. So the new method with the red points and a more naive method with the blue points. Now, in order to verify the theory, I did some experimental validation by putting the device on a test in a 3D Helmholtz coil, which is also temperature controlled, but in this case it just keeps the device at room temperature. And then I simulated 15 random device misalignments. And I say simulate because you can't actually rotate the device inside the Helmholtz coil. You actually have to apply fields under misaligned angles in order to simulate this misalignment. And then for the optimal calibration method, the new method, I determined the 3 Euler angles as well as the waveform parameters. And of course, for the more conventional naive method, you can't extract Euler angles because you have no information about the second harmonic at higher polar angles. So in this case, only the waveform parameters are extracted. And then for both methods, I extracted the angle error to compare them. Now here's a summary of the results. I would like to first point out the upper left plot, which shows the angle error as a function of the azimuthal angle for both the optimal and planar calibration, so the new method and the old method. And it turns out, so there are 15 lines each for the blue and the red ones because 15 misalignments. It turns out the optimal calibration performs slightly better. However, if you look at the standard deviation of those 15 lines, it turns out that there's almost nothing left for the new method, meaning that whatever is left as a systematic error in this plot can no longer be caused by device misalignment. And the situation gets even more pronounced at polar angles of 45 degrees, where the error is really strong for the planar calibration method, and this situation of 45 degrees could either be caused by very strong misalignment or by really strong stray field in Z direction. And if you compare the values in the table, it turns out there's almost a factor of 20 in improvement in angle error. So quite a high improvement for a strong stray field or misalignment. So in summary, I developed a new efficient calibration routine for 3D misalignment calibration. It improved the angle error, especially in the presence of a stray field, up to a factor of more than 20. And in the future, it would be interesting to include more parameters in the model. For example, temperature would be interesting. And it also could be interesting to apply the method to more sensors that kind of show a similar kind of response, for example, GMR sensors. And with that, I would like to thank you for your attention, and of course, I'm open for questions.